right now, if you're driving an electric vehicle, there's basically a controlled lightning storm happening just inches beneath your feet.
Yeah, that's a pretty accurate way to put it.
Right. Because your car's traction inverter is taking direct current from the battery, and it's rapidly switching it to create alternating current for the motors. We are talking about hundreds of volts and, hundreds of amps being manipulated thousands of times every single second.
Exactly. It's a staggering amount of energy just pulsing right there under the floorboards.
But here's the terrifying reality we are exploring today on this deep dive. If two specific cables inside that system connect for even a millionth of a second, the current spikes at a rate of 1 billion amps per second.
Yeah, it's catastrophic.
So today we're looking at the microscopic, deeply paranoid, and frankly brilliant engineering that stops your EV from literally detonating on the highway. We're getting deep into the functional safety and fault diagnostics of dual-motor PCS systems.
Right, and specifically, we're focusing on the absolute highest priority risk in these systems, which is the inverter shoot-through risk and hardware interlock.
Exactly. We're looking at 5 core dimensions of this, from the root causes to the hardware-software diagnostics, all the way to the design, manufacturing, and extreme validation. I want to break this down completely for you listening because the sources we've pulled together are effectively the holy grail of automotive functional safety.
They really are. I mean, if you have a milliohm level short circuit in your power stage,
Yep.
the silicon carbide switches, the Cines MOSFETs, they will suffer a lethal thermal meltdown.
Lethal thermal meltdown. Just that phrase alone is intense.
Oh, right. I mean, they go into an electrical avalanche in mere microseconds. The casing can rupture, the battery can be compromised, and you're practically guaranteed a total loss of vehicle control.
1 billion amps a second. Just trying to visualize that kind of energy release it's difficult. Let's start with the failure itself. You called it a shoot-through. Walk me through the actual anatomy of that event. We have the inverter, we have the motor. What is physically happening when this goes wrong?
Okay, so think about the basic building block of that inverter. It's called a phase leg or a half bridge.
Okay.
You have a massive semiconductor switch on the top, and that's connected directly to the high voltage positive terminal of your battery pack.
Yeah.
You have another massive switch on the bottom connected to the high voltage negative terminal.
And the output to the motor is right in the middle.
Exactly. It sits right in the middle between them. And they have to take turns.
Right. So the top connects the positive flow, then it shuts off. Then the bottom connects the negative flow.
And they have to do it in perfect alternating harmony. The motor relies on that, that alternating push and pull.
Makes sense.
But if that sequence overlaps, if the top switch and the bottom switch are ever turned on at the exact same moment, even for a single microsecond, you've just created a direct zero resistance bridge between the positive and negative poles of an 800-volt battery.
Oh, man, a dead short.
A completely dead short. And because there's virtually no resistance in that path, Ohm's law just takes over. The current tries to go to infinity instantly.
Wow.
That is the shoot-through. And according to the functional safety specifications we're analyzing, there are 4 distinct root causes that can trick or just physically force those switches into overlapping.
Yeah, and the first one detailed in our research completely blew my mind because it's a side effect of the very technology that makes modern EVs so efficient. We're talking about silicon carbide chips, right? And something called the Miller effect.
Yeah, the Miller effect. So silicon carbide, it's a miracle material for EVs. Compared to the older silicon IGBTs, silicon carbide allows for incredibly fast switching.
Which is good for efficiency.
Right, it reduces energy loss and gives you way more range. But that speed is exactly what introduces the danger. The spec notes that these MOSFETs can switch at a rate of greater than 10 kilovolts per microsecond.
Okay, wait, 10 kilovolts, that's 10,000 volts in a microsecond?
Yeah, and in extreme applications, that switching speed can hit 50 volts per nanosecond.
What does 50 volts per nanosecond actually do to a surrounding circuit? Because, on a human scale, a nanosecond is just incomprehensible.
It's violently fast. So think of voltage as electrical pressure.
Okay.
If the top switch turns on and suddenly applies 800 volts of pressure to the circuit in a matter of nanoseconds, the bottom switch, which is just sitting there in the off state, is suddenly hit with a massive wall of electrical pressure.
It's just sitting there, supposed to be closed, and it gets slammed.
Yes. And this is where the physical construction of the microchip itself becomes a huge liability. Inside that bottom MOSFET, between its different terminals, like specifically the drain and the gate, there are tiny, unavoidable pockets of capacitance.
And capacitance is just like a storing charge, right?
Yeah, right. Think of capacitance has a tendency to store and transfer electrical charge when the voltage changes.
Hmm.
One of these internal pockets is called the Miller capacitance.
Okay, so when that 800-volt wall of pressure hits the bottom switch.
That extreme rate of voltage change, which engineers call dVdt, it pushes a surge of current right through that internal Miller capacitance. We call it a displacement current.
Displacement current, got it.
And it bypasses all the normal control pathways and injects itself directly into the gate of the bottom switch.
You know, I was trying to picture this earlier, and I kept thinking about two heavy doors in a small, airtight room.
Oh, I like that.
Yeah, so you're standing outside one door, and you slam it shut with incredible force. Even though absolutely no one touched the handle of the second door, the sudden, massive change in air pressure inside the room forces that second door to just violently pop open.
That is the perfect way to visualize it,
Yeah.
honestly. The voltage spike is the slamming door. The displacement current is that invisible wave of air pressure,
Right.
and the bottom switch is the second door.
Right.
The gate of a MOSFET is the trigger that turns it on, right? It has a threshold voltage. If the displacement current pushes the voltage at that gate above the threshold, the switch just turns itself on.
It doesn't even matter what the car's computer is commanding at that point.
Exactly. The physics of the voltage spike have forcibly blown the switch open.
And boom, the top switch is on intentionally, the bottom switch gets blown open by the air pressure of the voltage change, the battery shorts out, and you have a catastrophic shoot-through.
Purely induced by internal physics.
Oh,
It's
what?
wild.
Oh, yeah.
But that's just the first root cause. The second one moves us away from internal capacitance and into something that sounds straight out of science
Oh,
fiction.
yeah. The cosmic rays.
Cosmic rays and clock glitches.
I seriously had to read this section of the documentation 3 times. It specifically discusses metastability, timer glitches, and single event upsets. It sounds like time travel.
I know, right? But it is a daily reality for functional safety engineers. So, that incredibly complex switching sequence we just talked about, it's choreographed by a central brain, a highly advanced microcontroller unit, or MCU.
Like the AURIX chips mentioned in the sources.
Yeah, exactly. The AURSTC3XX family. Inside these MCUs are complex timer modules whose entire existence is dedicated to enforcing a dead time.
Let's define dead time really quick for you listening, because that's crucial. It's basically the intentional pause, making sure the top switch is completely, totally off, waiting a tiny fraction of a second, and then turning the bottom switch on. It's a digital safety buffer so they never overlap.
Exactly. It's a rigidly programmed delay. The timer literally counts down before allowing the next action. But here's the vulnerability. The memory registers holding that timer data are made of microscopic silicon transistors.
Okay.
A cosmic ray, literally a high-energy particle that originated from a supernova across the galaxy, can travel through space, penetrate the Earth's atmosphere, go right through the steel chassis of your car, and strike the silicon lattice of that microcontroller.
That is so crazy. And what happens when a subatomic particle hits a microscopic transistor?
It generates a microscopic burst of electrical charge, basically electron hole pairs in the silicon.
Right.
And if that charge hits the specific memory cell holding the dead time value, it can cause what's called a single event upset, an SEU.
Meaning it flips bit.
Right. It flips a single bit of data from a 0 to a 1, or a 1 to a 0.
So a star exploded a billion years ago, and the particle it shot out just randomly overwrote the math in my car's safety computer.
Yeah, that is literally what happens. And if that bit flip changes the dead time register, the timer could instantly overflow, or just reset to 0. The intentional pause is just mathematically erased.
Wow.
So the software thinks it's perfectly safe to turn the bottom switch on even though the top one is still closing. The signals overlap, and the microcontroller inadvertently commands a shoot-through.
That is terrifying because it's completely invisible and seemingly random. But the source material also mentions clock glitches in this same category. Is that similar to the cosmic ray issue?
The result is similar, yeah, but the cause is completely terrestrial. Microcontrollers rely on oscillating clock signals to keep time, usually generated by a crystal circuit.
Right.
If there's electromagnetic interference or extreme temperature fluctuations, the internal clocks of different components on the board can experience a glitch. They slide out of phase with each other.
Like two musicians suddenly playing at different tempos.
Exactly. The digital logic gets confused, the timing constraints are violated, and again, the on and pulses overlap digitally.
Okay, so we have physical voltage spikes forcing doors open and cosmic rays scrambling the brain's timing. That brings us to root cause 3, ground bounce and parasitic inductance. We talked about voltage changing rapidly, dV/dt, but here we're talking about current changing rapidly.
Remember, an EV inverter is switching hundreds of amps. When you turn a switch on, the current doesn't just casually start flowing, it ramps up instantly.
And why is that a problem for the physical circuit board?
Because of parasitic inductance.
Right.
Every single conductor, every wire, every tiny copper trace on a printed circuit board has a tiny bit of inherent inductance. It's just a fundamental property of electromagnetism.
But it's usually really small, right?
Yeah. Under normal conditions, with low current, it's so small you just ignore it. But inductance resists rapid changes in current flow. When you try to shove a massive, instantaneous surge of amps through a trace, that tiny inductance acts like a dam.
And water rushing into a dam builds up pressure.
Precisely. And in electrical terms, that pressure is voltage. The formula is V equals L times DIT. Voltage equals inductance multiplied by the rate of change in current.
Okay, that makes sense.
This becomes incredibly dangerous in the Kelvin source wire. That's the tiny trace that connects the massive power module to the delicate control circuit. The sudden surge of current creates a localized voltage spike across that specific trace.
I was thinking about how to visualize this. Imagine a giant trampoline. You have a heavy person representing the massive power circuit and a toddler representing the delicate 5-volt control circuit, and they're both standing on it. The toddler is looking at the heavy person to gauge where flat ground is. If the heavy person suddenly jumps violently, the fabric of the trampoline stretches and warps.
No, I see where you're going.
The toddler loses their footing because their reference point for ground is violently shifting up and down.
That is an excellent analogy. The heavy person jumping is the bit surge. The stretching fabric is the parasitic inductance creating a voltage. And this phenomenon is literally called ground bounce.
Ground bounce.
Yeah, the ground reference for the massive power circuit violently shifts away from the ground reference of the control signals.
So the control chip thinks it's sending a 0-volt stay-off signal relative to its own ground. But because the power ground has bounced up by, say, 5 volts due to the inductance dam,
The switch looks at that relative difference, misinterprets the bounced ground as a 5-volt turn-on command, and opens up. The switch is essentially tricked into firing by localized electrical earthquakes on the board.
which brings us to the fourth and final root cause in this section. And honestly, I need you to clarify this one because it feels totally counterintuitive. The documentation outlines microvoids and isolation barrier breakdown in the gate driver chips.
Right.
But these are solid-state chips, right? They're sealed in hard epoxy. How does a sealed chip just break down?
Well, it's easy to think of microchips as indestructible black boxes, but they're physical structures, and they're subjected to brutal environments. Let's look at the role of a gate driver chip, like the ICE driver or the GD3100 families mentioned in our sources.
Okay.
They're the translators. They sit directly between the low-voltage brain of the car, the 5-volt microcontroller, and the terrifying 800-volt reality of the power switches.
They're just passing messages back and forth.
Yes, but they cannot let the circuits physically touch, or the 800 volts would instantly vaporize the 5-volt brain. So they use galvanic isolation. Inside the chip, they use microscopic magnetic transformers, or capacitive silicon dioxide layers, to send signals across a microscopic physical gap. It's like flashing a light through a pane of bulletproof glass to send a Morse code message.
Okay, so the message gets through, but the high voltage can't cross the glass. That sounds perfectly safe to me.
It is, unless the glass has a flaw. During the manufacturing of these chips, the silicon dies are glued and wire bonded, and then encapsulated in molding compound. If the curing process isn't absolutely perfect, microscopic voids, literally tiny bubbles of trapped air or gas can, form inside the packaging, right next to that isolation barrier.
Okay, a tiny bubble, but it's just air.
Yeah, but air is a much poorer insulator than the molding compound. And over time, as the inverter heats up to 150 degrees Celsius and cools down to sub-zero temperatures, the differing materials expand and contract at different rates.
Thermal stress.
Exactly. This thermal mechanical stress concentrates around those microvoids, creating microscopic stress fractures in the isolation barrier.
The bulletproof glass develops a crack.
Exactly. And the switching action of the inverter creates high-frequency common mode noise, which is basically aggressive electrical static. That high-frequency noise seeks the path of least resistance.
Right.
It finds those microvoids,
Yeah.
follows the stress fractures, and punches right through the isolation barrier.
And once the barrier is breached,
The 800-volt power side floods backward into the delicate 5-volt control side. The delicate internal logic of the driver chip is instantly overwhelmed and fused. It locks both the top and bottom switches into a permanent on-end state, creating an unrecoverable catastrophic short.
Okay, so let's summarize this absolute nightmare we are dealing with. We have extreme voltage changes forcing switches open through internal capacitance.
Yep.
We have cosmic particles from dead stars randomly erasing the safety timers. We have current surges turning the circuit board into a trampoline that tricks the sensors. And we have microscopic bubbles acting as Trojan horses for high-voltage floods. I mean, the physical universe is seemingly throwing every trick in the book at this inverter to make it explode. How on earth does a vehicle actually survive this?
This is the pivot point in functional safety engineering. You just have to assume the universe will cause these faults. And you design an architecture that can catch them and neutralize them before the energy destroys the vehicle.
Right.
So now we're moving into the four-ring defense system, which is a total masterclass in hardware and software co-diagnostics.
The four-ring defense. Okay, let's set the stage with the Automotive Safety Standard governing this, ACLD. That dictates the time limit we have to catch this.
The
Right?
Automotive Safety Integrity Level D. It's the most stringent risk classification. It defines a metric called the FTTI, the Fault Tolerant Time Interval.
FTTI, got it.
For an inverter system, the standard dictates that from the moment a fault occurs, the system has a maximum of 60 milliseconds to detect it, react, and bring the vehicle back to a safe state.
60 milliseconds. I mean, a human eye blink is about 300 milliseconds, so the car has to realize it's exploding, stop the explosion, and secure the motor in 1/5 of a blink.
Yeah, and that's just the vehicle level requirement. At the lowest hardware level where the switches actually live, the reaction time must be less than 100 microseconds. And some layers have to react in less than 1 microsecond.
Less than 1 microsecond. That's insane. Okay, let's dissect the fortress. Ring 1 is the MCU hardware dead time injection. The specification leans heavily on this.
Right, so we established earlier that dead time is the intentional delay between switching.
Right.
Ring 1 is all about making sure that delay is bulletproof.
Okay.
Microcontrollers timer modules, the GTM and DTM, they are hardware configured to force a 1.5 to 2.5 microsecond gap between signals. It is hard-coded into the generation of the pulse width modulation, the PWM.
But wait, you just told me a cosmic ray could flip a bit in that exact register and wipe out the gap.
I did, which is why Ring 1 utilizes layers of cryptographic and mathematical armor.
Okay, lay it on me.
First, the configuration registers holding that 2.5 microsecond rule are locked by a feature called safe end init. It's basically a read-only protection scheme. Once the car boots up and the motor starts spinning, the central processing unit is physically locked out of changing that specific memory address.
So even if a software bug causes the CPU to go rogue, it can't rewrite the safety rules.
Exactly.
But what about a cosmic ray bypassing the CPU and hitting the memory cell directly? Safe end init wouldn't stop a physical particle.
That is exactly what is countered by the background CRC check, the BGCRC.
How does that work? Is it just comparing copies of the data?
No, it's way more robust than a simple copy. A cyclic redundancy check uses polynomial division. The hardware takes the entire block of safety memory, treats it as a massive binary number, and divides it by a fixed polynomial key.
Okay.
The remainder of that division is stored as a checksum.
I followed the math, but how does it catch the bit flip in real time?
Because the BGCRC module is a dedicated piece of hardware that runs autonomously in the background, constantly scrubbing that memory space.
Oh, I see.
Over and over, millions of times a second, it recalculates that polynomial division. If a cosmic ray flips even a single 0 to a 1, the underlying binary number changes.
Right.
So the next time the division runs, the remainder won't match the stored checksum.
It detects the mathematical anomaly instantly.
Instantly, it throws a massive fault flag to the system before the timer even has a chance to execute the corrupted dead time. It catches the cosmic ray before the damage can manifest in the physical world.
That is incredibly elegant. But what if the error isn't in the microcontroller's memory? What if the ground bounce we talked about earlier tricks the sensor further down the line?
Yeah.
That brings us to Ring 2, the PCBA cross-coupled interlocks.
Right. Ring 2 abandons software entirely and relies on pure, unhackable physical wiring. On the printed circuit board assembly, the PCBA, the gate driver chip for the top switch, and the gate driver chip for the bottom switch are physically connected to each other. The input command pin of the high side is hardwired directly into the safety interlock pin of the low side, and vice versa.
I love this concept. Think of a nuclear missile silo, right? You have two launch key slots spaced 10 feet apart. The mechanical design of the system physically prevents one key from turning if the other key is in the wrong position.
Exactly.
It doesn't matter what the computer in the control room is screaming. The physical metal of the lock vetoes the command.
That is exactly how Ring 2 operates. Inside these driver chips, there's a dedicated hardware logic gate called shoot-through protection, or STP.
Okay.
It's constantly monitoring the hardwired pin coming from its partner. If the top switch is registering as on-N, the STP logic physically clamps the bottom switch's output down to 0 volts.
It just cuts the cord.
It bypasses the microcontroller entirely. If a ground bounce tricks the MCU into sending a simultaneous on-command, the cross-coupled interlock on the board receives it, looks at its partner, sees the conflict, and physically refuses to turn the switch on.
It's an absolute physical veto.
Yep.
Okay, so the software is mathematically armored, and the hardware has physical handcuffs. But we established in the root cause analysis that sometimes the command is correct, the handcuffs are in place, but a massive voltage spike simply forces the switch open through internal capacitance.
The displacement current.
Right, the physics bypasses the logic entirely. What catches that?
Then we enter Ring 3, which is definitely the most violent and time-critical layer of the defense. Ultra-fast desert protection.
Desat.
Yeah.
Yeah.
If rings 1 and 2 are bypassed, a shoot-through actually begins. The positive and negative rails connect. The current spikes toward infinity.
The billion amp per second scenario.
Yes. When a sync MOSFET is operating normally, like fully turned on, it's in a state called saturation. The resistance is incredibly low, so the voltage drop across the switch itself is tiny, maybe a volt or two.
Okay.
But when a massive short circuit occurs and thousands of amps try to force their way through, the switch is pulled out of saturation. It becomes a bottleneck. The voltage drop across the silicon violently spikes.
So the system uses that voltage drop as like a distress flare.
Exactly. The specification mandates a threshold, usually around 7 volts. The gate driver chip has a dedicated desat pin short for desaturation that is directly wired across the MOSFET.
Okay.
It monitors that voltage drop continuously. When it sees the voltage spike above 7 volts, it knows a catastrophic short is underway.
And it has to act fast.
It has less than 2 microseconds. For modern silicon carbide systems, it's often tuned to detect and react in under 1 microsecond.
Hold on, though. If the current is rising at a billion amps a second and it detects the short, why not just slam the switch closed as violently and quickly as possible to cut off the flow?
That seems logical, right?
Yeah, because the specs specifically mention a 2-stage soft turnoff, or 2LTO. Why soft? If a pipe bursts, you don't slowly close the valve, you slam it shut.
Well, actually, in heavy plumbing, slamming a valve shut is exactly what you avoid doing because of the water hammer effect.
Oh, okay.
Yeah.
Yes, the momentum of the water crashing into the suddenly closed valve creates a shock wave that bursts the pipe further down the line.
Exactly. And electrical current has momentum too, governed by that parasitic inductance we discussed earlier, V equals L times DIT.
Right, the inductance dam.
If you have thousands of amps flowing during a short circuit, and you brutally, instantly chop that current down to 0 in a nanosecond, the rate of change, the DIT, becomes astronomically high.
Oh, wow. And the parasitic inductance in the heavy copper bus bars pushes back?
It pushes back violently. The inductance reacts to that sudden cutoff by generating a colossal overvoltage spike. If you hard kill a 5,000 amp short circuit instantly, the resulting voltage spike will easily exceed 1,500 volts.
And what is the switch rated for?
Usually 1,200 volts.
So by slamming the door to save the chip from the current, you generate a voltage spike that literally shatters the silicon structure of the chip anyway.
Yep. You jump from the frying pan directly into the fire.
That is a brutal catch-22.
Which is why the 2LPO mechanism is so incredibly critical. When the desat pin detects the short, it doesn't just pull the gate voltage to 0 instantly. It steps it down to an intermediate level, say from 15 volts down to 8 volts, and it holds it there for a microsecond.
Okay.
This forces the MOSFET to act like a variable resistor, throttling the massive current down gradually. Then, in the second stage, it pulls the gate down to 0 to fully shut it off.
It bleeds the momentum out of the current so the inductance doesn't strike back.
It's a breathtaking balancing act.
Yeah.
It kills the short circuit fast enough to prevent a thermal meltdown from the current, but gently enough to prevent a voltage explosion from the inductance. And it executes this entire choreographed sequence in under 3 millionths of a second.
Wow. Okay, so the airbag has deployed, the switch survives, but now you have a car hurtling down the highway with a deactivated inverter. You've lost propulsion. What happens next?
So the driver chip has saved its own life, but it immediately signals the central brain that it's wounded. It pulls its fault, pins NFLTA and NFLTB low.
Okay.
This sends a hardware-level distress signal to the MCU's safety management unit, the SMU. Sometimes it's called the FCCU, the Fault Collection and Control Unit.
This is ring 4, the SMU fallback and safe path, the strategic retreat.
Exactly. Within 100 microseconds of receiving that distress signal, the SMU hardware severs the connection between the software and the motor control pins.
It just cuts the brain off.
Right. It locks out all normal PWM outputs. The brain is disconnected from the nervous system to prevent the software from accidentally re-triggering the short.
But the car is still moving, the wheels are turning, which means the motors are turning.
And that is the crux of Ring 4. The SMU has to make a split-second decision based on the vehicle's speed.
Yeah.
Because an electric motor is also a generator. If the car is moving at high speed, the specification defines this as greater than or equal to 7,200 RPM. The motor is spinning incredibly fast.
Generating a ton of electricity.
Massive amounts of back electromotive force, or BEM. If you just turn all the switches off and let the car coast, that spinning motor will act like a giant unregulated wind turbine.
Oh, no.
The voltage it generates will blast backward through the inverter's freewheeling diodes and spike the DC bus voltage so high it could overcharge and completely rupture the battery pack.
So you survive the microsecond short circuit only to blow up the battery a second later. How does the SMU stop that?
It triggers a stepwise active short circuit, or ASC.
Wait, it actively shorts the system.
Yeah.
We just spent 20 minutes talking about how shorts are the ultimate evil.
A shoot-through short across the battery is the ultimate evil. A short across the motor terminals is actually a controlled safe state.
Okay.
The SMU intentionally commands all 3 of the lower switches to turn on simultaneously.
Disconnecting the battery entirely, but connecting all the motor wires together.
Yes. But it doesn't stepwise to avoid a violent mechanical shock. First, it shorts just 2 phases together. This creates a magnetic buffer, suppressing the transient currents that could demagnetize a motor.
Got it.
Then, 1.5 milliseconds later, it drops into a full 3-phase short.
And what does that physically do to the motor?
It traps the energy. The current generated by the spinning rotor loops harmlessly back into the motor's own stator windings instead of blasting into the battery.
Wow.
It creates a massive electromagnetic drag, effectively acting as electronic brake. It securely clamps the chaotic back voltage to a safe level. The spec mandates keeping it under 720 volts.
It uses the motor's own magnetic field as a cage to trap the dangerous energy. That is genius. But what if you're stuck in traffic, moving at like 5 miles an hour?
Well, at low speeds, less than 2,000 RPM, the motor isn't spinning fast enough to generate a dangerous back voltage. If you were to trigger an active short circuit at that speed, the sudden electromagnetic braking force would cause a violent mechanical jerk.
Which could be dangerous.
Yeah, it could break the axles, shear the gears, or cause the tires to totally lose traction.
So the SMU looks at the tachometer and chooses a different path.
Right. It triggers active open circuit, or AOC. It totally kills all gate signals and keeps them off. It just disconnects everything and lets the motor freewheel to a stop.
It assesses the kinetic energy of a 2-ton vehicle and dynamically selects the physics required to diffuse it safely. So summarizing the 4-ring defense, we have mathematically scrubbed dead time timers, physical cross-coupled hardware handcuffs, a microsecond soft shutdown airbag that manages parasitic inductance, and a kinetic-aware strategic retreat that cages the motor's energy. It is an absolute impenetrable fortress.
It is a phenomenal reactive system.
Yeah.
But, you know, as any seasoned functional safety engineer will tell you, a great defense system is amazing. But it's infinitely better if the fortress walls are too high to climb in the first place.
Right. Why rely on an airbag if you can engineer the car so it never crashes?
Okay.
Which transitions us beautifully into the engineering blueprints. Section 3 in our research covers DFMEA design failure mode and effects analysis. Essentially, how do engineers proactively design these risks out of the physical circuit board before it's even manufactured?
They look at the root causes we discussed and attack them at the fundamental level of physics. Let's look at Prevention Strategy 1, which directly targets that slamming door displacement current caused by the Miller effect.
Okay.
The design standard mandates the use of active Miller clamps, or AMCs, combined with negative bias.
Let's break those down. First, negative bias. What does that actually mean in practice?
Normally, to turn a MOSFET off, you just drop the gate voltage to 0. You remove the pressure.
Yeah.
But in this extreme environment, 0 volts isn't a tight enough seal. The specification requires the gate to be actively driven down to -5 volts.
So you aren't just letting the door swing shut, you are actively pulling it closed and holding the handle down.
Exactly. You're creating a 5-volt negative buffer. The displacement current from a voltage spike has to overcome that entire negative 5 volts before it even reaches zero, let alone the positive threshold required to accidentally turn the switch on.
That makes total sense. But what is the active Miller clamp?
The AMC is the ultimate trapdoor. Inside the gate driver chip, there's a secondary, extremely low impedance internal switch connected directly to the gate of the MOSFET.
Okay.
During the turnoff sequence, once the gate voltage drops below a safe threshold, usually around 2 volts, the AMC aggressively activates.
And what does it do?
It creates a massive zero-resistance short circuit directly between the gate and the source terminal of the MOSFET.
Going back to our analogy of the airtight room, the 800-volt spike slams the first door. The invisible wave of air pressure, the displacement current, comes rushing toward the second door, threatening to blow it open.
But just before the pressure hits the door, the AMC opens a massive trapdoor in the floor right in front of it.
Oh, nuts.
All that nasty displacement current gets sucked straight down the trapdoor, routed safely to the ground. It completely bypasses the sensitive internal capacitance of the switch.
The pressure wave just vanishes.
Yep, the AMC actively neutralizes the DVDT threat. But what about the DDD threat?
The parasitic inductance.
Right, the parasitic inductance that causes ground bounce and makes the water hammer effect so dangerous during a shutdown. That brings us to prevention too. Low-inductance sandwich bus bars.
You said earlier that every single piece of metal has parasitic inductance. How do you design a blueprint without inductance? You can't just tell physics to stop working?
You can't eliminate it, true, but you can force it to cancel itself out using spatial geometry.
Okay, how?
The DC bus bars are the massive copper plates that carry hundreds of amps from the battery into the inverter modules. If you just run 2 thick copper cables side by side, they generate massive magnetic fields that create high inductance.
So how do you change the geometry?
The blueprints dictate a tightly laminated layout. They take the wide, flat positive copper plate and the wide, flat negative copper plate, and they sandwich them incredibly close together.
Like how close?
They're separated only by a microscopic layer of high-grade dielectric insulation, like Kapton tape.
A literal sandwich of high voltage. Why does being close together help?
Because of the direction of the current. The current in the positive plate is flowing towards the inverter. The return current in the negative plate is flowing away from the inverter.
Right.
Because the currents are moving in exact opposite directions, the magnetic fields they generate are also in opposite directions.
And because the plates are sandwiched so tightly together.
The opposing magnetic fields overlap and almost entirely cancel each other out. It's called mutual inductance cancellation.
Wow.
The design goal dictated by the spec is to squash the total parasitic stray inductance of the entire power loop down to under 15 nanohenries, with engineers desperately pushing for 10 nanohenries.
15 nanohenries. I don't even have a frame of reference for how small that is.
It's practically nothing. But it is the physical foundation that makes Ring 3 possible. Without that laminated sandwich geometry canceling the magnetic fields, the inductance would be so high that the soft turnoff couldn't bleed the energy fast enough. The V-spike would destroy the switch. Geometry basically saves the physics.
Okay, what about the digital side? The cosmic rays we can't stop, obviously. But what about the internal clock glitches that scramble the dead time timers?
That is addressed in Prevention 3. Hardware phase-locked clocks. A traditional circuit board might have several different chips, each with its own internal oscillator ticking away, trying to keep time.
Like having 5 people in a band all tapping their feet to their own internal metronome. Eventually, someone rushes the tempo.
Exactly. Thermal variations cause those individual internal clocks to drift. To stop this, the blueprint dictates that the MCU and all external critical circuits must share a single, incredibly precise, low-jitter external crystal oscillator.
One master conductor for the entire board.
Yes, a single heartbeat. But it goes further. They use hardware phase-locked loops, PLLs. These are analog circuits that constantly compare the phase of the incoming master clock with the chip's internal operations.
Okay.
The PLL dynamically adjusts the internal timing to ensure it perfectly matches the master heartbeat.
It physically forces everyone to step on the exact same millisecond.
Yep. The spec requires this system to keep clock phase errors tightly below 0.5 degrees. By enforcing absolute synchronized timing at the hardware level, you completely eradicate the setup and hold time violations that cause the dead time logic to glitch.
So we have trapdoors for displacement current, magnetic canceling geometry for inductance, and a master conductor for the digital logic. What about the microvoids, the tiny bubbles that let high voltage punch through the isolation barrier?
That is Prevention 4. If the fundamental threat is high-frequency noise punching through the barrier, you mandate vastly stronger barriers. The DFMEA dictates the mandatory use of gate driver chips with a common mode transient immunity, or CMTI, of greater than 100 kilovolts per microsecond.
Let me contextualize that. Earlier, we said the silicon carbide switches max out at a switching speed of 50 volts per nanosecond, which is 50 kilovolts per microsecond.
Precisely. The blueprint requires the isolation shield to be rated for double the maximum possible violence of the sword striking it.
Over-engineering at its finest. But the specification notes that the chip can't maintain that massive CMTI rating on its own. It relies on external filtering components, specifically mentioning Class 1 C0G, also known as NP0, ceramic capacitors, and thin film resistors with a 0.1% tolerance. Why such insane precision on basic resistors?
It really comes down to thermal drift and electrical symmetry. To maintain that 100 kilovolt per microsecond shield, the filtering circuits on the high voltage side and the low voltage side of the barrier must be perfectly balanced.
Okay.
They must have exact mathematical symmetry to reject the common mode noise.
But the inverter gets extremely hot.
Right. It cycles from sub-zero to 150 degrees Celsius. Normal capacitors and resistors change their electrical values when they get hot. It's a material property.
Oh, I see.
If the components on the top side of the chip drip slightly differently than the components on the bottom side, the symmetry is broken. The shield drops.
The armor develops a crack simply because it got warm.
Exactly. Class 1 COG ceramic capacitors are formulated with specific titanium dioxide dielectrics that have virtually zero temperature coefficient.
Meaning they don't drift.
Right. They do not change their capacitance value, regardless of how hot or cold they get. By mandating these specific, highly expensive materials, the engineers guarantee perfect mirror image symmetry across all temperature ranges, keeping the CMPI isolation shield intact.
So the blueprint is flawless. We've neutralized the physics at the design level, but here's where reality intrudes. A perfect CAD drawing is completely useless if the factory builds it wrong.
Yeah, that's always the catch.
If a worker drops a screw or a machine applies too much pressure, the perfect blueprint becomes a bomb.
That is the harsh reality of manufacturing. And it brings us to the fourth dimension of our deep dive, the perfect assembly line, or PFMEA process failure mode and effects analysis.
Right, so how do we ensure that the theoretical perfection of the blueprint becomes a physical reality?
You eliminate the human variable. Reading through these assembly line controls, the factory floor building these traction inverters sounds more like a Class 100 semiconductor clean room than a traditional greasy automotive plant.
Totally. Let's look at Control 1, 100% 3D X-ray and SAM void gating. This goes back to those microvoids we just talked about.
Right. When you assemble these power modules, you aren't just snapping Legos together. You are bonding raw silicon dies to ceramic cooling substrates using advanced processes like silver sintering or vacuum soldering.
Okay.
The goal is to create a perfect thermal and electrical interface. But during that melting and cooling phase, trapped flux gases or uneven pressure can leave tiny pockets of air voids inside the solid metal joint.
And as we learn, voids concentrate thermal mechanical stress and cause the chip to crack under high voltage.
Exactly. So you can't just inspect the outside of the part. Every single inverter board that comes down the line goes into a sealed chamber for 3D automated X-ray inspection, AXI, or scanning acoustic microscopy, SAM.
They use sound waves to look inside solid metal.
Yes, SAM uses ultra-high frequency ultrasonic transducers. It shoots sound waves into the solder joint and listens to the echoes. Solid metal reflects sound differently than a pocket of trapped air.
That's wild.
The computer built a high-resolution 3D map of the inside of the solder joint based on those echoes.
What are the pass criteria? How much air is allowed?
The rules are incredibly draconian. Total voiding across the entire thermal interface must be less than or equal to 5%. More importantly, no single contiguous void, no individual bubble, can be larger than 1% of the total area.
What happens if the machine scans it and finds a single bubble that is like 1.1%? Does a red light flash so an operator can pull it off the line?
Oh, they don't rely on an operator noticing a light. No, the inspection machine is tied directly into the manufacturing execution system, the MES, which controls the physical conveyor belt. If the acoustic scan fails by 0.1%, the MES physically locks the track.
Whoa.
The bad part is automatically routed into a quarantine bin. It cannot physically proceed down the assembly line. The process aggressively roots out the risk of thermal mechanical failure before the part is even finished.
That is ruthless. Okay, Control 2 covers a different physical assembly stress, laser alignment, and force displacement pressing.
Inverters have massive copper pins terminals that carry hundreds of amps that had to be inserted into the direct bonded copper, the DBC ceramic substrates.
Mm.
If an operator just jams them in, or if the factory uses a simple pneumatic press that just pushes until it hits a stop,
It applies uneven pressure.
yes. And ceramic is brittle. An uneven press creates microscopic, invisible fractures in the ceramic substrate.
Which is a ticking time bomb.
Exactly. Those microfractures might pass electrical testing at the factory, but after a year of vibrating over potholes, the crack propagates, the isolation fails, and you get a shoot-through.
So how do they press them in safely?
They use highly advanced servo presses guided by laser alignment systems. As the servo motor pushes the pin into the board, it monitors the exact force displacement curve in real time, sampling data every millisecond.
It's graphing exactly how much resistance the pin is meeting at every micrometer of depth.
Exactly. It knows exactly what the mathematical curve of a perfect smooth insertion looks like. If the pin encounters even a fraction of a newton too much resistance, indicating that it might be slightly crooked or scraping the edge of the hole, the servo stops the insertion instantly.
Amazing.
It halts before the stress reaches a threshold required to crack the ceramic. It performs microsurgery on a heavy industrial scale.
That leads perfectly into Control 3, which sounds much more mundane on the surface, but the specifications are just as intense. Torque angle fastening and optical scanning. We are talking about tightening the bolts that hold the high-voltage bus bars together.
It sounds mundane, but a loose high-voltage bolt is one of the most statistically significant causes of EV fires.
Right, because a loose connection means less surface area touching. Less surface area means high electrical resistance. And pushing 500 amps through a point of high resistance generates immense localized heat.
Exactly. It causes thermal runaway, the plastic melts, the battery short circuits, and the car catches fire. So guaranteeing a tight bolt is paramount.
But doesn't a mechanic just use a standard torque wrench? You pull it until it clicks, which means it reached the right tightness?
A simple torque click is nowhere near reliable enough for an ASIL-D safety system. Think about what torque actually measures. It measures rotational friction. If a single thread on the bolt is slightly stripped, or if there's a speck of dirt in the hole, the friction spikes. The wrench will click, telling you it's tight, but the bolt hasn't actually clamped the metal plates together yet.
Oh. It hit the friction limit, but it didn't travel deep enough.
Right. So the factory uses programmable servo screwdrivers running a torque angle algorithm. It measures the rotational force, but it also measures the exact number of degrees the bolt turned to achieve that force.
Oh, that's smart.
If it hits the torque target, but it only turned 180 degrees instead of the required 360 degrees, the system knows the bolt is jammed, not tight. It fails the part.
It guarantees the mathematical clamping force, not just the friction. But the spec also mentions optical character recognition, OCR scanning. Why are they scanning the bolts?
Because the friction coefficients of the bolts themselves matter. Different coatings, zinc, phosphate, bare steel, have different friction levels. If you use the wrong coated bolt, the torque angle math is thrown off. So before a bag of bolts is even loaded into the robotic hopper, an OCR camera visually scans the barcode and the lot number on the bag to guarantee it has the exact required phosphate-coated finish.
And what is the ultimate goal of all this bolt anxiety?
The spec defines it clearly. The contact resistance across that bolted joint must remain less than or equal to 5 microohms.
5 microohms. We're measuring physical connections in millionths of an ohm. What happens if it's, say, 1.3 milliohms instead?
At 500 amps, a 1.3 milliohm resistance generates over 300 watts of waste heat concentrated in an area the size of a dime. It will melt the surrounding insulation within minutes. Maintaining that micro-ohm level is the difference between a safe drive and a catastrophic fire.
Okay, the board is perfectly soldered, perfectly pressed, and perfectly bolted. Control 4 is the end-of-line test, the EOL, the final exam before it goes in a box.
The physical build is complete, yeah, but the system has to verify that the digital brain is properly armored. The EOL testing machine hooks up to the inverter's communication port and executes a cryptographic hash handshake.
It's interrogating the brain.
It is actively pinging the microcontroller, asking it to report back the exact configuration of its dead time registers. It wants to know that ring 1 of our defense system, the digital moat, is perfectly configured and locked by the safe and init protocols.
And how does it verify it?
It uses a 100% two-way cryptographic handshake. The MCU generates a hash code based on its internal safety memory and sends it back.
Okay.
The EOL tester compares that hash against the golden standard cryptographic library code. If there is a single bit out of place, if the hash doesn't match perfectly, The MES steps in again.
It outright refuses to print the shipping label?
The inverter effectively ceases to exist to the logistics system. It cannot leave the building. It ensures that no module leaves the factory unless both its physical construction and its digital safety logic are mathematically flawless.
So we have the mathematically perfect blueprint and a ruthless, automated, acoustically and optically monitored assembly line that guarantees the physical execution of that blueprint. Which brings us to the final and, frankly, most dramatic part of this deep dive.
The testing.
Yeah, Section 5, trial by fire, or DVP&R production validation. Because honestly, I have to act as the skeptic here. You can run all the computer simulations you want, you can have the cleanest factory in the world, but how do we actually know the car won't explode when it hits a pothole in a blizzard?
Yeah.
You can't just trust the math, you have to physically prove it, right?
You have to push the physical hardware to the absolute breaking point, subject it to the worst possible abuse, and watch it survive. That is the Design Verification Plan and Report, the DVP&R process. And Test 1 is the most brutal demonstration of confidence imaginable. The Type I and Type 2 shoot-through tests.
The intentional short circuit.
Yes. Following the rigorous AQG 324 qualification standard for power modules, engineers take a fully functional, perfectly built inverter off the line. They hook it up to a massive 800-volt power supply. They put it in an environmental chamber and heat the silicon up to 150 degrees Celsius, the absolute maximum operating limit. And then they intentionally command a shoot-through.
They literally pull the pin on the grenade and hold it just to see if their own blast shield holds.
They do it twice, actually, to test different states of vulnerability. Type I is a static test, performed before the system fully boots. They manually hold the top switch permanently open and then forcefully command the bottom switch to fire.
Inducing a dead short from a standstill.
Exactly. Type 2 is even more aggressive. They run the inverter dynamically, switching a massive electrical load at 15 kilohertz, simulating the car accelerating hard. While it is rapidly switching, they inject a digital fault that forces the on-end signals to cross over mid-cycle.
You are injecting a catastrophic failure into a running, heavily loaded inverter. What are the pass criteria? How do you know it survived?
The internal systems, specifically that Ring 3 dust tap protection we discussed, must independently catch the fault and trigger the two-stage soft turnoff in less than 1.5 microseconds.
It has to prove the microsecond airbag works under live fire.
And it has to prove the water hammer physics were managed correctly. During that violent shutdown, they use high-speed oscilloscopes to measure the voltage spike caused by the parasitic inductance.
Right, the V spike.
For a component rated at 1200 volts, the spike cannot exceed 1000 volts. It must prove that the soft turnoff successfully throttled the current without causing a lethal V spike.
And what about the silicon itself? Does it get damaged?
That is the final, most critical criterion. Zero EOs, zero secondary electrical overstress burns. After the grenade goes off, they take the module apart and examine the silicon carbide under a microscope.
And it has to be clean.
It must be pristine. No avalanche breakdown marks, no microscopic melting, no degradation of the gate oxide. The system must survive the ultimate failure, completely unharmed and ready to function again.
That is incredible confidence in the engineering. But a shoot-through is a singular microsecond event. What about the long-term reality of being bolted to the chassis of a car? You have freezing winters in Minnesota, boiling summers in Arizona, and thousands of miles of vibrating, terrible roads.
That leads directly to Test 2, which engineers affectionately refer to as shake and bake. It's formally based on the ISO 16753 standard for automotive environmental testing.
How do you simulate a decade of bad roads?
You accelerate the aging process through extreme violence. They take the inverter and bolt it rigidly to a multi-axis electrodynamic vibration table. They shake it with a frequency sweep ranging from 10 Hz up to 2,000 Hz, pulling a constant 35 meters per second squared of G-force.
That is nearly 3.5 Gs of continuous, high-frequency, bone-rattling vibration.
While it's shaking, the table is sitting inside a thermal shock chamber. They rapidly cycle the ambient temperature from deep winter negative 40 degrees Celsius up to a scorching positive 150 degrees Celsius.
Wow.
And they leave it in this state, vibrating and thermally expanding while running high power through the circuits for over 500 solid hours.
What exactly is that targeting? What fails under those conditions?
They are specifically hunting for vulnerabilities in the coefficient of thermal expansion, the CTE. We talked about this with the microvoids. The ceramic substrate expands at a different rate than the copper bus bars, which expands at a different rate than the silicon chips, which expands at a different rate than the solder holding it all together.
So as the temperature swings wildly, the materials are physically fighting each other, pulling and tearing at the joints. Add 3.5 Gs of vibration, and you are trying to literally rip the solder apart.
Exactly. They are trying to force microfractures to propagate. And the pass criteria after 500 hours of torture are impossibly strict. The electrical resistance of those main solder joints can only increase by a maximum of 1.2 milliohms.
1.2 million.
Any more than that indicates the internal crystalline structure of the solder is tearing. Furthermore, during the entire 500-hour test, absolutely no control signals, not a single one, can drop out or glitch for more than 1 microsecond.
It has to operate flawlessly while being shaken to death, and I saw a note in the specs about a destructive physical analysis after the test.
Yes, the DPA. Passing the electrical tests isn't enough. They take this inverter that just survived 500 hours of torture, and they take a precision diamond saw and literally cut the circuit board and the power modules in half.
They destroy it to prove it survived.
They polish the cross-section and put it under a scanning electron microscope. The engineering team must physically prove, visually, that there are exactly 0 micro cracks propagating through the solder layers or the ceramic substrates. It must be structurally perfect on a microscopic level, even after a lifetime of simulated abuse.
The irony of cutting it in half to prove it's indestructible is wonderful. Okay, so the physical hardware is proven. What about the final software safety net? Ring 4, the SMU logic that actively shorts the motor at high speeds. How do you test that without blowing up a real test track?
That is test 3, the 12,000 RPM virtual crash. It relies on advanced hardware in the loop, or HIL simulation.
How does HIL work for something this powerful?
Well, they don't hook the inverter up to a real motor, because the forces involved would be too dangerous to test repeatedly. Instead, they hook the physical inverter up to a high-fidelity FPGA supercomputer.
Okay.
The FPGA mathematically simulates the exact electrical behavior, inductance, and back electromotive force of a real motor, spinning at a maximum speed of 12,000 RPM under full load.
The computer basically tricks the physical inverter into believing the car is going flat out on the Autobahn.
Exactly. And then, the test engineers inject a digital fault that intentionally bypasses the physical hardware interlocks we discussed in Ring 2. They force the software to manifest a shoot-through condition digitally.
It's like intentionally throwing a massive wrench into a jet engine while it's at maximum thrust, just to watch the internal computer systems react.
And it must react perfectly. The safety system must recognize the fault, realize it has been bypassed, step in within its 60 millisecond FTTI window, usually executing in under 100 microseconds, and trigger that stepwise active short circuit.
It has to intentionally short the spinning virtual motor to cage the energy.
Yes. The HIL rig measures the simulated physics in real time. The test proves 3 things. First, the DC bus voltage must be successfully clamped to under 720 volts, ensuring the battery doesn't explode.
Okay.
Second, the short-circuit braking current circulating inside the motor windings cannot exceed 550 amps, ensuring the motor doesn't melt.
And third.
Crucially, the mathematical model must prove there's absolutely no demagnetization of the motor's permanent magnets. If the active short circuit applies too much opposing magnetic force, it will permanently strip the flux from the magnets, and the motor will be destroyed forever.
So the system has to catch the microsecond fault, gently throttle the current using the soft turn-off to avoid the water hammer, assess the speed of the vehicle, actively short the motor to cage the energy, and smoothly brake a 12,000 RPM rotor, all without degrading the internal magnets.
Only when it passes that simulated crucible, along with the grenade tests and the vibration torture, is this architectural design considered safe enough to be manufactured and put into your family's driveway.
Wow.
Automotive ASIL-D is arguably one of the most demanding engineering environments on the planet because you're dealing with lethal amounts of electrical energy in an entirely uncontrolled consumer environment.
As we wrap up this deep dive, I am just trying to synthesize the sheer layered complexity of what we've covered. We started with the quantum mechanics of displacement currents forcing switches open and cosmic rays from dead stars flipping binary bits. We moved into cross-coupled physical hardware handcuffs and microsecond airbags that bleed off parasitic inductance. We explored trapdoors in the blueprints, magnetic canceling sandwich geometry, and perfectly symmetrical thermal drift capacitors.
It's a lot.
We watched robotic lasers perform microsurgery and acoustic microscopes hunt for microscopic bubbles, and it all culminated in intentional high-voltage explosions and 500-hour vibration vibration torture tests. It really is a massive symphony of physics, software, material science, and extreme validation, all dedicated to a single, hyper-focused goal, keeping the power switches in an EV from destroying themselves.
It is a monumental achievement of collaborative engineering. It takes hundreds of specialists across dozens of disciplines to make this work. But I want to leave you with one final staggering concept drawn directly from the technical specification, something that highlights the sheer scale of the math involved.
So definitely, please do.
Think back to the electromagnetic shock wave of a short circuit. We talked about DID, the rate of change in current. In a full catastrophic failure, that current rises at a rate of 10 to the ninth power amps per second.
1 billion amps per second.
1 billion amps per second. To truly perfect the Ring 3 defense against an event that's incredibly fast, the engineers don't just guess at the timing of the two-stage soft turnoff. They don't just pick a microsecond and hope the water hammer effect doesn't blow up the chip.
So how do they figure it out? Trial and error.
At a billion amps a second, trial and error would just result in a room full of vaporized silicon. They use advanced Python programming to build what they call high-resistivity, multi-pin, parasitic inductance transient models.
What does that actually mean?
It means they computationally map the exact microscopic resistance and the exact spatial inductance of every single millimeter of copper trace, every single aluminum bonding wire, and every single droplet of solder on the board in 3D space.
That's crazy.
They simulate the subatomic geometry of the physical metal itself, running thousands of transient mathematical permutations, just to calculate the mathematically perfect, exact fraction of a microsecond required to trigger the soft shutoff.
They simulate the atomic structure of the metal to mathematically beat a billion-amp shockwave. That is astonishing.
It represents the absolute pinnacle of predictive physics. So, next time you are accelerating onto the highway in your EV and you feel that smooth, entirely silent rush of power, take a moment to consider the invisible lightning storm raging inches away from you.
I definitely will.
Consider the billions of calculations, the quantum physics, the perfectly torqued bolts, and the microsecond fail-safes actively fighting off the chaos of the universe before you even feel the G-force push you back in your seat.
A microscopic battle for survival, 1 millions of times a second, just so you can enjoy the ride. I love that. Thank you so much for joining us on this deep dive into the engineering that keeps us safe. Keep looking beneath the surface of the technology you use every day because, as we've seen, the real magic and the truly staggering engineering is always hidden just out of sight.